Greece, a coastal nation steeped in ancient history and mythology. A dynamic, volatile landscape prone to earthquakes and erupting volcanoes. And for some, the perfect environment for developing new techniques to search for life on the ocean worlds of our solar system.
If you look at oceanography, particularly when you're dealing with the deep ocean, these are areas that humans aren't designed to go to.
Meet Dr. Richard Camilli, research scientist from the Woods Hole Oceanographic Institute and NASA's Network for Ocean Worlds. Dr. Camilli and his team are here off the coast of the island of Santorini to deploy a fleet of autonomous research vehicles and explore the volcanically active seafloor below.
The ship is right over the site of the Callisti Limnes. My colleagues and I discovered this site back in 2012, and it's interesting because it has subsea pools of fluids that are from the volcano here. These pools represent an environment that may have existed here on Earth before life really took hold.
Greece is a very nice place to study geology, because it is a kind of a supermarket of natural disasters. So if you want to be a geologist and you need to study geology, you need to visit Greece. And of course, we are talking about Santorini. Santorini is being connected with all the myth of Atlantis and the sunk city and the city that has been destroyed of the volcanic eruptions. And that's why we are using marine technologies to explore the seafloor, and we need to know more and more about this volcanic history of Santorini.
The goal of this program is cooperative exploration with under-actuated vehicles in hazardous environments. And what that means is that we have robotic vehicles that are effectively autonomous or semi-autonomous. And so that decreases the need for human interaction and control of the vehicles. And so that these vehicles can work cooperatively in order to explore areas that are dangerous, potentially too dangerous or too far away for humans to go.
So I've always been struck at how parallel ocean exploration and space exploration is. That space exploration is one about collecting data about science, but it's also when you're not in communication, right? In Mars, for example, you can communicate once a day. In the ocean, it's very similar, right? Once you go through the surface, you can't communicate. So somehow you have to embody the key insights of a scientist to be able to look at for, is that evidence of life? Where do I go to kind of answer the next question? So I think it's really a driver for embodying a level of scientific reasoning that we've never seen in explorers before.
To give this power of reasoning to their fleet of vehicles, the team took a page out of their favorite TV show, Star Trek, and created a suite of algorithms called Enterprise. The lead algorithm, Kirk, oversees the total mission and communicates with other algorithms, like Spock, who oversees the science objectives.
Basically what we're doing is we have scientists on board the ship that are feeding information, basically policies, to these automated planners that then take those policies plus the information. Some of it is historical information in the oceanographic context. Some of it's new information being transmitted by the vehicles here and now. Takes all that information, combines it to construct a mission that gets to the scientific deliverables while also being safe in terms of vehicle survivability, but also being safe for the environment where they're operating.
Currently in a deep space mission, there are mission planners and people who execute missions, but those are humans. They plan an engineering sequence of commands, and then they send that to the vehicle. What we're talking about here is the system being able to do the planning on its own and have it doing that planning on board. And then the other part is automating the science. So if we look at recent Spirit, Opportunity, Curiosity, they have some demonstrations of detecting interesting scientific events and adapting to it. Our systems build upon that idea, but they go to the next level in terms of saying, how can the vehicle constantly analyze its data, right, without human intervention and decide where to go to discover interesting science, and then allow the scientists guide and shape that as they consider to be appropriate.
They have to be smarter, they have to be more agile, they have to be able to interpret their environments correctly, diagnose faults, overcome them, basically adapt to their environments in order to complete their missions.
Ocean expeditions are huge collaborative endeavors between the crew, scientists, and engineers. Let's meet some members of the team.
My name is Mario Fernandez. I work for the Woods Hole Oceanographic Institution. I'm a mechanical engineer with the group, and I work mostly with the ROV Jason system and a little bit with the other deep submergence vehicles. What it means to be a deck boss on a ship or a launch coordinator is pre-planning how you're going to safely deploy and recover the ROV we have on board. There's a lot involved. We have to control an A-frame, winch, crane, taglines to control the load while it's on deck. A lot of potential to go wrong. Tagline slips, line breaks, you have a 5,000-pound wrecking ball. I believe we have a total of 8 or 9 people it takes to properly control the vehicle as it goes over and comes back on. And we want to make sure everyone's coordinated so we can do it safely.
My name is Molly Curran. I'm here with Woods Hole Oceanographic Institution. And on the ship, I am a mechanical engineer for ROV Nereid Under Ice. The hybrid ROV that we call NUI is still a young vehicle. It's a constant challenge trying to make it the best that we can make it. My favorite part about these expeditions is that they're all different and they all have their own challenges. We come to these crazy parts of the world to do these expeditions that are working with new technology, finding new science, working with some of the greatest scientists in the world, the greatest engineers, and bringing all of these people together on one ship. You've got a lot going on and a lot of cool stuff happening, a lot of incredible science and cutting-edge technology all coming together. It's really fun.
My name is Casey Machado. I work for Woods Hole Oceanographic Institution, and I am a research engineer. My work involves design and operation of robots to explore the world's hardest to reach places in the ocean. On this current expedition, I am the expedition leader for the ROV team and the pilot for the Nereid Under Ice vehicle. My favorite part of this current expedition was getting to explore inside a volcano. I've never dove into a volcano before, and there were lots of breathtaking views in terms of both the super steep cliff faces and then all of the CO2 venting hydrothermal activity. I'd never seen anything like that before, so anytime I see something new, that's always something that's exciting to me. Being able to explore places that other people don't have any way to really access, and I can bring these images and samples to the public at large. It's an honor and just an incredibly interesting responsibility to have.
Before sampling can begin, Spock needs to collect more data about the area. Enter the gliders.
The gliders play an important role in the missions, kind of very parallel to a NASA mission. If you look at a Mars mission, first thing that we did was that we sent in reconnaissance to get an overall view, and that's an orbiter. The next thing is that we had Spirit and Opportunity and Curiosity. Those are moving around and trying to find interesting geological sites. And then Mars 2020 and beyond is a sample return. So you can think of what we're doing here as being very parallel, that the ship is like the orbiter and is giving us a broad view of the Colombo volcano, right? Once we do that map, then we need to be able to explore interesting places to collect samples. So the gliders are navigating around places that look promising from what the ship told us, and then it looks to identify places where we might want to send NIRI. And then finally, NIRI is very capable in terms of doing the samples, but it can't move around nearly as much. And so we finally put NIRI at the places where the gliders thought that they were interesting.
The gliders are super energy efficient. The battery pack we've got in there and the instruments we've got on, it could run for probably a week to 2 without needing to recharge it. That's because it makes the trade-off of being slow, not very maneuverable, and having instruments that have reduced fidelity, and not having constant communications with the surface. Douglas, we're ready to launch the gliders. So yeah, that's the trade-off really made, is that we've got this super energy efficient vehicle that can go out there for a long time, but it's not very capable. But that's not to say that it can't do things, right? We do have some nice sensors on there. One of the most interesting ones probably is the temperature sensor for this use case. With that, we can actually detect temperature anomalies. And so that helps us kind of localize where maybe there's a vent here. And that's really the concept of operations for these gliders, is that we can put them in the water. They can be essentially the forward scout.
The gliders that we were using, we sent them down into an active volcano. Some of the areas that they were traversing through were incredibly complex and dangerous in terms of vehicle survivability. I guess the best analogy would be like hang gliding in Midtown Manhattan at night, where you can't see in front of you except maybe with a light that would travel the distance of a flashlight and navigate in amongst the buildings. The fact that we were able to do that with a vehicle that takes roughly the same amount of power as a cell phone and traverse these areas and map these areas is a big step forward, because in order to move into some of these ocean worlds in our solar system, we will have to have vehicles that are smaller, lighter, and lower power.
Kirk and Spock, equipped with the latest information and data collected from the gliders, are now able to create a mission plan for the main star of the show.
The ROV that we have out here is a unique ROV in that it's a hybrid. It's not just an ROV, but it also has the capabilities of an AUV. We deploy the vehicle with a fiber optic tether that then gives us communication to the vehicle. We have onboard batteries, so there's no power going through the tether, only communication. And from that, we're able to have HD video and control the vehicle like a typical ROV from the ship. But as you can imagine, with fiber tether, at one point it might break because it's quite delicate and we're going hundreds or thousands of meters into the ocean. And once that fiber breaks, the vehicle then has the brains to become an AUV. At that point, it can continue a mission pre-programmed into the vehicle, or it can come to the surface and we can tell it where to go. We can say, stay at a safety distance, and we'll tell you acoustically what to do from there, or it can continue on as an AUV and do some sort of pre-programmed mission.
Safely deployed into the sea, NUI sets out on its mission.
There's always a bit of tension in the operations where do you go strike out in an area that is unstudied and potentially come back with nothing? Or do you go to a site that you know and try and understand it a little bit more, that kind of incremental advancement? And so what Spock did was it picked out areas that it thought was interesting that were completely unexplored. We have a group of scientists on board that are very skilled and knowledgeable, and they had some sites that they wanted to go back to. So initially there was a little bit of tension where they said, well, why can't we go just take a left here and it's just right over there. We could be there in a half hour and we're sure to get some great samples. We stuck with the Spock program and it paid great dividends, and all of the scientists were amazed at what they saw. The first site that we went to was spectacular. The second site we went to was spectacular. Each of the sites, of the 5 sites that it identified as interesting, were interesting, and they were each interesting in a different way. Totally different environments. Getting that buy-in is difficult for technology because you're effectively asking scientists to retool to use this new improved mousetrap when they are perfectly comfortable using their existing mousetraps.
All the work we do with the ROV is a huge collaboration between the operators and the scientists. And we always like to say that in the end, we're, as an ROV team, working for the scientists because our goal is to enable them to do the kind of research that they need to do.
The reason this site at the Colombo volcano is important to us is that it's a good representation of what we might expect in ocean worlds if we were going, for example, to explore Europa. We're interested in looking at life in extreme environments, which are likely to be in places where, for example, you might have vent holes or kind of what we'd see in a volcano.
The sampling process involves first identifying a target that's of scientific interest on the seafloor, and then using the manipulator arm on the vehicle to move whatever tool it is, be it the slurp sampler or a push core or just picking up a rock or something like that, and then actually technically executing it and performing that series. And it's sometimes challenging and you sometimes have to be creative with it, but that's an aspect of it that I really enjoy. It's always good to see excitement on a scientist's face when you actually get the sample finally.
These environments also contain organisms that can fix carbon dioxide without photosynthesis. That's super important if you're far off in our solar system where the sunlight is weak and potentially you may be under a liquid ocean as well.
Pretty much all ROV operations currently involve a pilot looking at camera feed or a series of camera feeds and trying to use a joystick to control the manipulator to where they want to go. So it's very direct pilot control of every single joint on the manipulator. Kind of an intermediate step from that is shared autonomy, where you could imagine a pilot indicating a desired pose for the arm to move to, but then a planner taking over and coming up with the path that the arm should move to reach that goal. And then the pilot just essentially hitting a button and the arm following that path. And so they don't actually have to directly control every joint from a joystick. Then eventually we want to get to the point where we could send one of these vehicles to an ice world, Europa, wherever it may be, and when they go under the water, they're gone. Like, we have no communication, we have no human feedback. So in that case, they need to operate without any human intervention. So they need to be able to understand the scene through perception, and then make a decision about how they want to manipulate to take a sample or achieve a task. First of all, you get increased safety. So a lot of issues dealing with these kind of vehicles is scientists want to put different sensors, different payloads. The tool sled is always changing. You might have different things mounted on the vehicle. One thing I've seen in the past is where the vehicle configuration gets changed and the pilots are kind of used to a certain configuration and they forget that they've added this new thing to the vehicle, and then you end up whacking something, you can damage expensive sensors. The other benefit you get is you can massively speed up the manipulation tasks because the system can generate a plan much faster than a human can by just kind of visual servoing, operating direct joints to move the arm where they want to go. If you can imagine that you have a precise estimate of your tool poses, of your scene reconstruction, we have many algorithms that are very good at planning a path for these kind of manipulators, and they can then execute these kind of tasks much faster. This is the first time we've actually tried to use the perception to actually control the manipulator to do something significant. I think the most interesting thing we were able to show is that we could project the reconstruction from the stereo pair into the frame of the vehicle. So you could have a 3D visualization of the ROV and its door configurations with the manipulator, and it gives you this kind of 3D perception that you don't get from just looking at these 2D camera feeds that the pilots usually drive from. Oh, new point cloud. Wow, look, we just opened up a lot of stereo vision. So now if I tell it to take sample, it should move down onto the T-handle. So we were able to project the point cloud into that scene and then command the arm to grab a push core and move it into a location within that 3D reconstruction. We verified that that location matched up. So that showed the viability of an autonomous system where you could say, sample the biomat that you see in this reconstruction, and it could do the full task without any input. this work that we've done here, we've really seen some of the areas where we really need to focus and adapt autonomy for underwater specifically. There's problems that you run into that you just don't face terrestrially, especially when it comes to perception and you're dealing with different water properties, bubbles filling the scene, they get reconstructed as solid objects, or you kick up dust and then you no longer have any perception. So how do you work with these uncertainties? But in the end, you'd have to develop an autonomous system that was capable of recognizing those kind of failures and adapting to some kind of compromise to still achieve a task.
For me, as the PI on this program, it's not only exciting but satisfying to see that we were able to complete these missions and get data not only for the robotics research side, but also for the biologists and geologists, so that they have greater insights into the volcano and the life forms that exist there. Back in 2012, when we discovered these Callisti limnes, these pools on the seafloor, we had absolutely no idea what they were at first. We thought they were brine pools. It turned out they weren't. They were of a completely different composition. But another aspect that we did not understand was how long they existed. Were they ephemeral, or did they last on geologic timescales? And we know now, after the dive today, that these pools are ephemeral. And what that means is that the organisms that are living there have to match the dynamics of the geology. And we saw that there were active fumaroles on the seafloor. We've never seen that before. But basically it means that the life has to follow the dynamics of the environment in the same way that in the desert, when it rains, it blossoms. And so it may be the case that when these volcanoes become active, the life blossoms around them. So it's really amazing to see that today. It's answered a question for us, but it's led to several others. The next step for me personally is to push further on this autonomy so that we include greater and greater sensing capability for the vehicles and to make inferences and estimate where the most important science areas are to operate. They are intended to improve our abilities to go and explore these other planetary bodies, the ocean worlds, the moons of Jupiter and Saturn. But additionally, we can use that information to help understand our Earth right here.
As humanity continues to explore the furthest reaches of our solar system, our robotic explorers will need to be more intelligent, thinking for themselves and adapting to situations in real time. NASA scientists will continue to study and explore Earth's ocean in preparation for the day when we land on the surface of an ocean world and search for signs of alien life.